Today I want to talk about this concept of momentum and this other concept of impulse and find the relationship between them. There is a link that we can prove later in the video. Now, do not confuse momentum with inertia. Inertia is the property of matter to resist the change in its state of motion, meaning like either rest or moving. Momentum, I would like to describe it as the quantity of motion. So I'll give you some simple examples to help you understand this idea. So let's just take a tennis ball and a bowling ball, right? And they're both going at the same speed, 5 meters per second, okay? Now, which one you think will cause a bigger damage if it touches something? Well, obviously it has to be the bowling ball because it's heavier. Okay. Now if I take the lighter ball, right, but this time I make it go extremely fast, and I make this go extremely slow. So you can see that this lighter ball, will create a bigger damage. We say that it has a greater amount of, or greater quantity of motion. So you can see that this quantity of motion that I'm trying to describe, it's not just speed, okay? It's definitely, it has to do with speed, but that's not the only factor that affects it. You can see that speed and mass both play a role. And as a matter of fact, they play an equal role. Okay, so this quantity of motion, what I mean, is proportional, directly proportional to the velocity, and it's also directly proportional to the velocity. So if I want to measure this quantity of motion that I'm going to call momentum, here, my formula that I'm going to come up with is, that I'm going to define is P for momentum, don't ask me why, okay, equals M times V. Now, we have to understand that momentum is a vector quantity. Momentum is a vector quantity. Okay, which means that it has magnitude and direction is also important. Which means that when we have something going at an angle, now we'll be doing momentum in 2 dimensions. You can do momentum in 3 dimensions, but you can pretty much do everything in just 2 dimensions if you choose your plane correctly. So we're going to be dealing with momentum in 1 dimension now, just along the x-axis or the y-axis, it doesn't matter. And then later in the unit, we'll just do a 2D problems with momentum. Okay, so if I take a bullet, a small bullet, right, that has, let's say, 10 grams and going at 6,000 meters per second, and if I want to compare its momentum to the momentum of a bowling ball that has a 6 kilogram mass, but only going at 1 meter per second. If you do the math correctly here, and obviously you have to change your grams to kilograms, the standard units still apply. You have to be in kilograms here, and you have to be in meters per second for the velocity. These two will have the same exact momentum by the time you finish, when you do your MV. And again, it's 1-dimensional, no angles here. All right, the next thing I want to talk about is I can take an object here and I can apply force to it for a certain amount of time, and I can get it to go from a certain speed. Let's just start with 0, and we'll do a demo in class. Let's just say it's starting from 0, or rest. I'll just write rest here. Okay, and I want to eventually get that object to go at a velocity of, let's say, 30 meters per second, or just V. Okay. Okay, and this has a mass M. Okay. So I can do this in an infinite number of possibilities, right? I can do it by applying, and we'll see this in class. I can apply a small amount of force, but over a very long period of time, right? I can increase my force by a little bit, but I don't have to apply it for as long as I did before. Or I can just give it a kick okay? In other words, apply a huge force for a small amount of time. So you can see that the possibilities are infinite, okay? So this idea of applying a force over a period of time is called impulse. An impulse, again, we don't call it I, we call it J, is also a vector quantity. If you think about it, you're going to apply a force in a certain direction. So force is a vector. Time is not. But if you multiply the time, which is a scalar, and the force, which is a vector, you should end up with a vector quantity. So this concept of impulse should have to do with the force applied and the duration of the force that's applied. So I'm going to define it as F times T, or delta T. Now, force is the force applied. The T, you just have to be careful here, and I'm going to emphasize this. The T is the time during which the force is applied. In other words, is the time it takes to change the velocity from a certain number, it doesn't have to be a rest, to a different value. And it could be either speeding up or slowing down, by the way, right? So if you're slowing down, you should have a negative impulse because the force will be lower in your magnitude of velocity, okay? So these are the two equations that we're going to be dealing with here. Okay, and I'm going to do some demonstrations in class to show you what I mean by applying a small force over a long period of time and a big force over a short period of time. So J, which is impulse, equals F, force applied. T is the time during which the force is applied. I say that at least 3 times in the last minute, so make sure we understand that. Because it will be times where you might be confused about which time to choose, but that's the time during which the force is applied, okay? Okay, so now let's see if there is a link actually between these two ideas. Now, obviously you can see that the change in momentum, if momentum is to change, it's not because of the mass changing, but because of the velocity changing. I hope you can see that. Okay. You can't change the momentum, okay, by changing the mass. The mass remains constant. Okay. So now let's see if we can do the derivation. Now I'm going to start this with Newton's second law. So I'm going to say F net equals m times A. Now, I know that A is delta V over T. The time it takes to make that change in velocity, to create that acceleration. So what I'm going to do here, I'm going to take, and you take this note under derivation, okay? I take that T and I multiply it by both sides. So I get TF equals m delta V. Well, so I'm going to put it nicely here as FT, okay? M delta V. Well, I know that m delta V, I just defined it, is basically delta P. And this is all vector quantities, by the way. But if it's one-dimensional, it doesn't matter, okay? Equals, now, m delta V, I can just say that it's m final velocity minus initial velocity. Now, what's delta P? If you want to write delta P here, this is just going to be P final minus P initial if you want to add that extra equation. So when you're looking at your equations, when you're trying to solve problems, I want you to write this whole formula and keep everything together. And the reason for that, because there will be times where you'll have to use, depending on what's given and what you're looking for, you might have to use this first part of this equation and this fourth part. You might have to use the first and the second. So if you have it all in front of you, it should be pretty easy to see which equation to pick. If you put it on like multiple equations, like 5 or 6, whatever you have there, then you will be maybe confused. So that's what I recommend. If you want to do it any other way, be my guest. Okay? All right. So let's see what this does. Now, I'm going to concentrate just on this first part. All right. Excuse me, I have a cold. Okay, so I'm going to concentrate on this, and I'm just going to say it's in one dimension, so I'm just going to get rid of this. We'll worry about the two-dimension stuff another time. All right, and this is impulse, by the way. Okay? Okay. Now, when you play sports, I'm going to use an example of baseball or softball. All right? Okay, let's just say when you hit the ball, okay, you want it to have as much speed as possible when the contact between the bat and the ball is lost. Okay, so you want to, the moment it leaves, the contact is lost, you have no control over it. So what you want to do, you want to make sure that the moment it's going to leave with the greatest possible velocity. So what you want to do in sports, you want to increase this delta V. Right? You have no control over the mass, right? So the bottom line is that if you want it to go really far, you have to maximize this, okay? In order to maximize that, you have to come here. You control this stuff, right? You control the force, and you control how long is the force applied. Again, how long is the force applied has to do with how long the force is applied has to do with the contact time between the bat and the ball. It has nothing to do with the time that the ball stays in the air. You have no control over that. The only force acting on it at that point is just gravity becomes a projectile. So what can you do to increase this? You have two things you can do. Okay, and you want to do both. You want to hit it as hard as you can, and you want to extend the contact time, which means you want to follow through, right? That's why we follow through in baseball. So you want to hit it and keep the contact as long as possible. Okay. So, but there are times where you don't want to have a big force. Okay. You want to. Okay. Let me just make sure I talked about that. Yeah. There are times in collisions you want to lower the force. Okay. So if you want to lower the force, let's see what you can do. And I'll give you an example. Let's say you have two people, or one person, same person, right? Okay, and they're going to jump, let's say, from the second floor of the school. So let's just say that's about 3 meters. I remember that because we did the stairs lab. It's about 3.5 or so. All right. So they have two options here. They have grass here, okay, or this concrete and grass. Okay. Now, if they just drop, right, and whether they land on grass and whether they land on concrete, you can see that the velocity right before they hit the ground is going to be the same for both of them. You can do that with kinematics, like the free fall stuff, or you can do that with conservation of energy. Okay? Either way. So the velocity before impact or at impact is the same. The collision does not happen while they are in the air. That's why I said you have to be careful about which time to pick. The force of impact, which is going to be up, is resisting your motion, right? The force is only happening at impact. So the change in velocity is between going from a certain velocity right before hitting the ground, which we can calculate, by the way, right? And stopping, because you don't stop right away. It takes a fraction of a second for you to stop. Okay, so now you can see that the delta V, okay, whether you land on grass or concrete, is the same. In other words, you're going to go from a certain speed, which we can calculate. I can do mgh is half mv squared. So we don't care about the mass of this person. So we can say that v is equal to radical 2 times 10 times 3. So what is that going to be? So it's a radical 60. Okay. So here you're going to go from radical 60 to 0. That's the change. While here you're also going to go from radical 60 to 0. So the change in velocity is the same. The mass is the mass of this person. So really you have no control over this, okay? So the impulse in both of these cases is the same. Is the same change in velocity and is the same mass. Okay, now let's see what happens to the force at impact. When you're landing on concrete, okay, the amount of time it takes you to go from radical 60, which is close to 7 point something, right, to 0 is very short. And the reason for that is because concrete does not give, right? So the amount of time that it takes to stop is extremely short. And it's usually in the milliseconds, okay? Or even less sometimes. It depends on the collision on the surface. So on grass gives, right? So which means it's going to take you a little longer, right, to go from radical 60 to 0, okay? So let's see what happens here. So on concrete, this is constant basically in collisions, right? This is different than when we play baseball, the baseball example earlier. So if this is constant, if you're landing on concrete, you have a very small amount of time. Well, if you want to keep this product constant, okay, you're going to end up with a big force. And that means that this force applied to this person when they hit the concrete is big, so which means they might get hurt, okay? And they will get hurt. 3 meters is pretty high. Okay, if they land on grass, the time here is still short, but compared to the time it takes on concrete is longer, which means the force is smaller now. I hope we can understand this idea in collisions. Okay? Okay. So whether you land on grass or on concrete from the same height, the same mass, your impulse will be the same. So let me make sure what the next idea I have to do. Okay. All right. So that's why in cars, okay, when there's a collision, right? So let's say it's going to hit a wall here, let's say, right? Okay. So if it's going to hit a wall, what they do with the cars, they want to make sure that when it hits the wall, okay, it takes a longer time. So this car can be going at 20 meters per second, right? And it's going to come to a stop when it hits that wall. So they want to make sure that when it hits the wall, it takes the longest possible time to go from 20 to 0, right? So because if you can accomplish that, if you extend the time, you lower the force, okay? So what they do in the cars, they have this crumple zone. So basically what it is that the front of the car crumples, right? And extends the time to go from 20 to 0, which means you have a smaller force acting on the car and on the passengers. All right. Well, the next thing is like we're going to talk about the impulse for a force that's changing, because here I talked about force that's constant. So here, if I do an FT graph, if I can graph that, right? And let's say if the force is constant, okay, and this is time, and this is a certain amount of time t, and this is your force F here. Well, the impulse we say is just Ft. So it's basically, if you think about it, it's just this area here, and we've done stuff like this in the past. This is for a constant force. Well, I can extend this idea to a force that's changing. So let's say during a collision, the force does that. Okay? Okay. So which means you have to find this area here to find the impulse, J, basically, right? So the impulse here for a varying force, J, for a variable force equals area between curve, usually lines or segments or whatever, a curve and time axis. Okay, and in this case here, if the same as before, if this curve happens to be down here, you have to look at that as a negative impulse. So let's look at an example. Okay, so let's say I have an object here moving at it has a certain impulse J, right? Or a force, I guess. So let's do force. and this object here is at rest. Okay? When the collision happens, right? Let's say if I'm able to record, and we'll try this in class, I'm able to record the force produced during this collision as a function of time. And let's say that force looks maybe something like this. Okay? And it lasts a very small amount of time, in milliseconds. So let's just say it lasts 10 milliseconds, right? And the force is 100 newtons. I'm just making up numbers here. Force basically here in newtons. Okay. The impulse delivered, okay, is going to be this area, which is 1/2 base times height. So that should be 500. Now, if you look at the units, if you're looking at the units for impulse, it's force times times. So times time is newtons times second. For momentum is mv, so kilograms times meters per second. So this object here, we're going in this direction, so J is in that direction. So if I look at right as positive, it's going to experience an impulse of 500 newtons times seconds. Okay. Okay, well, what does this one experience? Well, if this one hits this one that it's at rest with the force to the right, it's going to feel, in other words, this one is getting the force to the right. Okay, this one is going to feel a force to the left. Okay, because of the action-reaction, Newton's third law. Okay, Newton's third law. Okay, so if the impulse that this one feels is to the left, negative J, right? Okay, so which means that the graph, if you can graph this, it will look down here. So just keep that in mind because we're going to need that for the future to do problems. Okay. All right. So let's see what we can do here. So I'm going to try an example. So this one is going at 5 meters per second. It has a mass of 10 kilograms. Okay. This one is, let's just say, has a 5 kilogram mass, and it's at rest. So I'm going to try to figure out the collision lasts 0.01 seconds. Okay, so I'm going to do the impulse. So J equals, and I have a graph here for the force. So F T, and this lasts, I'll make it easier so that I can divide. So 0.02 seconds and a force of 100 newtons, right? Okay, so J is going to be basically this area here. So that should be 1/2 base, right, times the height. So assuming that's a triangle, right? So what is that? So that should be just 1 Newton time second. Okay. The graph for this one will, the graph for this one will be like that, assuming that the right is positive. For this one, it will be down. All right, so impulse equals change in momentum, right? So I can figure out by how much will the momentum of this one change. Here it has a momentum of 50 kilograms meters per second. Okay. Okay, so let's see by how much it's going to change. It has to be less at the end, I think, right? All right, so J for this guy is -1. It's not 1. For this one, it's 1. Equals the change in momentum. Well, the final momentum is what I don't know, minus its initial momentum, which is 50. So I have to subtract that. So if I do the math correctly here, the final momentum should be 49. The momentum for this guy is going to be J equals change in momentum. Now the J for this one is +1 equals the final momentum. Okay, and it started with no initial momentum. Okay? All right, and that should do it. All right, I'm out. Peace.